We're always hearing about how AI is getting more and more powerful, right? But how? How does that actually happen? Well, it's not just about building bigger computers. The real story is this incredible journey of scale, one that starts in the microscopic world inside a single chip and zooms all the way out to satellites orbiting the Earth. Think of it like an infinite ladder. And in this explainer, we're going to climb it together. So this is the central question we're trying to answer. As these AI systems get bigger, it's not a simple case of just adding more processors and getting a little more speed. The real magic, the part that's so fascinating, is how each new level of scale unlocks entirely new abilities, multiplying performance in ways you wouldn't expect. This question right here is going to be our guide. Okay, so to make sense of this whole journey, we're going to break it down into 5 distinct domains of scale. This is our roadmap. We're starting with scale in. That's deep inside the silicon, and then we're going to zoom out level by level all the way to scale above, which, you guessed it, takes us beyond the planet itself. So let's get started at the very, very beginning with the chip. Right, our first section is all about the absolute foundation of AI power. I mean, before you can even think about building massive data centers or global networks, you have to get the fundamental building blocks right. And that means focusing on the silicon chips themselves. This is where the whole quest for massive computational power really begins. So this first domain is called scale in. Here's a good way to think about it. Imagine you're building a city. Before you can build skyscrapers or lay down highways, what do you need? You need the perfect brick. Scale in is all about designing that perfect, insanely powerful brick, optimizing every little thing within the silicon and its immediate packaging. And the complexity here at this microscopic level is just mind-boggling. You see, a key priority here is first silicon success. And that's because making these chips is so incredibly expensive and takes so long that it has to work perfectly the very first time. There are literally no second chances. Engineers also have to figure out how to integrate multiple smaller chiplets. These are tiny specialized pieces of silicon, all onto a single package. You get this foundation wrong, and nothing else up the ladder is going to work, period. Okay, so we've designed our perfect brick. Now what do? We scale up. This is where we take all those powerful chips and start assembling them into a single, super dense structure. So if scale in was making the brick, scale up is building the skyscraper. It's all about packing as much power as you possibly can into a server rack and making sure all those parts can talk to each other at unbelievable speeds. At this stage, the absolute crucial piece of the puzzle is the interconnects. We're not just worried about one chip anymore. We're focused on the fabric that connects thousands of these specialized AI processors, like GPUs or TPUs. The priorities become validating unbelievably fast data links. I mean, look at these numbers: 800 gigabits, 1.6 terabits, even 3.2 terabits per second. It's all about making sure these processors can communicate at absolutely blistering speeds. And to put that kind of speed into perspective, right now, engineers are moving data at 224 gigabits per second on a single lane inside the rack. That's like downloading dozens of high-def movies in 1 second. It's insane. And they're already planning for double that speed. This is the kind of data fire hose you need to keep all those AI chips fed and working inside our computational skyscraper. So we've built our skyscraper. Awesome. But a single skyscraper doesn't make a city, does it? The next logical step is to build the entire district. We're now zooming out from a single rack to the scale of an entire data center, connecting thousands of these powerful racks into one giant, cohesive machine. Now, this represents a really fundamental change in thinking. Scale up was all about maximizing the bandwidth inside the rack, building vertically. But scale out is all about creating a perfect, flawless network between all the racks. The engineering problem completely shifts from vertical construction to horizontal city planning. And this is the scale out domain. Honestly, this is the level that makes today's giant AI models possible. See, normal internet traffic usually flows north-south, from users on the internet to the data center. But training a model like GPT-4 creates these massive, swirling storms of east-west traffic, where thousands of processors are constantly chattering with each other across the entire cluster. This fabric has to be designed specifically for that kind of workload. So the goal here is to make these thousands of GPUs act like a single giant brain. And that means you have to maximize GPU utilization. You can't have these incredibly expensive chips just sitting around waiting for data. That requires a super stable, lossless fabric and really predictable job completion times. It's just a massive orchestration challenge, making a city-sized computer think as one. All right, now we take our next giant leap. We've built our AI city district, it's humming along, but what if we need to connect it to another city, maybe in a totally different region? We are now moving beyond the physical walls of a single data center and thinking about how to connect these powerhouses across entire continents. Welcome to Scale Across. If Scale Out was city planning, then Scale Across is like building the national superhighway system. This is all about linking different data centers, whether they're across town or across the ocean, using these ultra-high-capacity optical fabrics. The challenge now is totally different. It's about sending enormous amounts of data over very, very long distances, with as little delay as possible and with maximum reliability. This needs specialized tech, like these coherent optical modules, which are basically superpowered transceivers that can blast massive amounts of data through fiber optic cables across continents. The ultimate goal is to make the physical distance between data centers totally irrelevant. So we've built our connected civilization of AI cities. What could possibly be left? Well, we scale above. This is the final frontier, taking AI infrastructure beyond terrestrial limits. If we built the superhighways, this is like establishing a global air traffic control and satellite network for our AI civilization, connecting every single point on the globe and, yes, even reaching into space. In the priorities here, they sound like something out of science fiction, but I promise you, they are very real problems being solved right now. We're talking about the super low latency 5G and 6G networks needed for things like self-driving cars to make split-second decisions. It's about having real-time AI everywhere. And yes, this even includes non-terrestrial networks and orbital data centers, literally extending the reach of computation into space. Okay, wow. We have climbed the entire ladder from the chip all the way to the stars. So why does it even matter? Why break AI scaling into these 5 specific domains? Let's zoom out one last time and really look at the big picture. This quote right here, this is the key to everything. As you move from one domain to the next, you're not just solving the last level's problem. Each new level of scale fundamentally changes the game. It unlocks entirely new capabilities that were literally impossible before. Going from a chip to a rack to a data center isn't just an increase in quantity. It is a fundamental change in quality. So here's the big takeaway. Scaling AI is this incredibly complex, multi-layered challenge. As we've seen, the engineering problems you have to solve for a single chip are completely different from the ones you solve for a global satellite network. By mastering each of these 5 domains, one by one, we systematically expand bandwidth, we crush latency, and we extend the reach of AI from a tiny piece of silicon to a truly planetary scale system. Which leaves us with one final kind of mind-bending thought. We've scaled from the chip to the rack to the data center, across the globe, and even into space. We basically achieved planetary scale. So as we look at this seemingly infinite ladder of progress, you have to wonder, what's the next rung?